All right, let's get started. First off, just so everybody's aware, and the folks who are in concrete design are all too aware of this, but we were having some very significant issues on the AV side, particularly with this monitor. It just decided to turn off and on. That was a good try. It was a good try, but shucks. But I've got a good feeling that it's going to work, so we'll see. Okay, so if you remember, I said that my goal is to have the exam graded on Monday, but senior design takes precedence. Yeah, they didn't get graded over the weekend. That just didn't happen. For those of you that are in senior design, I'll go ahead and tell you, I've got the reports edited. I just need to type out my edits and upload them. And my goal is to do that by the end of business today. I just have to find some time to sit there and do that. I decided I thought it would be a good idea to put this up on the slide so that everybody can have this. And I had it on a previous slide, but now that the exam's over, I guess our attention can get diverted a little more towards getting out of this class, right? And what's the path towards the end. So we have 3 homework assignments left. You have one right now that's due on the 15th of April. That's on columns and frames. And then we have 2 homework assignments on beams. One's on continuously braced beams, and one's on discretely braced beams. And after today, I think you will understand the difference between those two. Today, what we're going to do is we're going to go back to that concept of a plastic moment and go back to this section property of ZX. And we're going to go through an example where I compute ZX. Now, just so everybody's aware, I'm also on the side going to compute, well, what is SX? What is the section modulus? Now, everybody in here should know how to do that. At the very least, I showed you how to do a lot of this stuff in mechanics of materials or reinforced concrete design. So you've done it with me at some point or another. I'm not going to make you compute SX, but I want you to see the difference. And then once we do that, we're going to talk about capacity, and specifically about how do discretely braced beams differ from continuously braced beams, both from a code standpoint and from a capacity standpoint. And so I think you'll kind of get an idea of where this is headed after this lecture. So with that, let me just jump right into it. Now, I know I'm tempted to show my animated slide again because it's just awesome, but I'm gonna just sort of move past that. The big thing I wanted you to take away from the last lecture is that there is a difference between, first off, the yield moment, which is the moment at which the extreme fibers start to reach the yield stress, and the plastic moment. The plastic moment meaning where every fiber along the cross-section reaches the yield stress. So because of that, we have now new definitions for a centroid. We sort of, we have what we're calling a neutral axis. We have 2 different terms. Sorry, if this is in the way, I'll move it. What's that?
Now I have a
No, they do. We have an elastic neutral axis. Now, the elastic neutral axis is what everybody in here should be familiar with. That's just where the centroid is. But the plastic neutral axis is specifically defined as where the compressive forces equal the tensile forces. Now, here's the big deal about that. For the most part, we're going to be dealing with homogeneous cross-sections. In other words, cross-sections where the steel is all of the same grade. Okay, so this is so we'll be able to split that plastic neutral axis off from a force standpoint and just look at the section properties, and that's where ZX comes into play. Now, the big thing is, does the elastic neutral axis and the plastic neutral axis occur at the same spot? Not necessarily. It does when there is an axis of symmetry. So, for instance, if I have a doubly symmetric I shape, the elastic neutral axis and the plastic neutral axis are in the same spot. But when they're not symmetric, you know, if you have a flange up top that's bigger than the one down below, that location changes. And I'm going to show you that in an example today. Now, How do you compute where the plastic neutral axis is and what is this property ZX? Well, if you're dealing with a cross-section that's all of the same material and it all has the same yield stress and what have you, then the plastic moment is really just the forces times that moment arm. And so that force is going to be a stress Fy times that area. And so it's just areas times moment arms. In fact, the plastic neutral axis is where compression equals tension. But if you're dealing with the same material, then it's really where the area above equals the area below. And that's not necessarily the same thing as the plastic section, or as the centroid. So I want to go through this example. Computing where the plastic neutral axis is and the ZX property is really straightforward, and I think you'll find that after today. So I have a cross section. I have a 12 times 1.5 inch top flange, an 18 by 1 1/4 web, and a 16 by 1.75 inch bottom flange. Now I put this on this Excel sheet here because I'm going to do some Excel calcs later. I'm not going to make you repeat them. I just want to show this. Let me put this on my notebook here. Okay, so I'll give you all a sec to draw this out and say, this is example, is this 19? Okay. Now, so what we're going to try and do is compute ZX for this. Okay. Now, in order to do that, we have to determine the location of the plastic neutral axis. Now, the plastic neutral axis is that magical line where the area above that line equals the area below that line. So in order to do this problem, we have to make a guess. Okay? To start, we have to ask ourselves, do we think that the plastic neutral axis is going to be inside the flange, inside the web, or inside the bottom flange? You tell me, what do you think is the most reasonable guess? The web. Yeah, that's a pretty straightforward guess. Okay? So what I'm going to do is this. I'm going to assume that the plastic neutral axis is somewhere in the web. Okay. Now, I have no idea where that is. I'm just going to assume it's somewhere there. So you all have had algebra before, so when you have an unknown, we'll call that unknown x. So what we're going to say is this. We're going to say that this dimension here is x. So I have no idea where it is. We'll just figure that out here in a second. Now, if this is x, what is this dimension below? What is that? No, if this is x, what's this? No, it's 18 minus x, right? Because think, if x is, I don't know, 6 inches, then this is 12 inches because it's 18 minus that. So this is 18 minus x. So I'd argue this part right here is actually the hardest, is actually setting this part up. Okay? Now, what we'll do is we'll assume positive bending, so everything above the neutral axis is in compression. Everything below the neutral axis is in tension. Okay? So let's see if we can define what is the area in compression. So the area in compression is this area right here, all this red shaded area right there. So what's a good formula for this? Somebody help me out. What's the area of the flange? There we go, 12. And for the sake of this, I'm going to keep everything's in inches, so I'm just going to leave that off. 12 times 1.5 plus what? 1.25 times x, because the thickness is 1.25. So that's 1.25 times x. Is everybody okay with that? So chugging that out, what's 12 times 1.5? Say it again. 18. So this is 18 plus 1.25x. Now, what's the area in tension? What's a formula for this, this green shaded area right there? So let's start off with the flange. What's that? Plus what? There we go. So 1.25, 18 minus x. So let's break out that, distributive property. It's like the whole foiling thing, right? So 16 times 1.75 is what? Say it again. 28 plus, and then 1.25 times 18 is? Say it again. 22.5 minus 1.25x. So 28 plus, bless you, plus 22.5, that's 50.5, not 40, I was going to say 40. 50.5 minus 1.25x. Okay? So the location of the plastic neutral axis is wherever C equals T, or wherever that area above equals the area below. So therefore, AC equals AT, so that's 18 plus 1.25x has got to equal 50.5 minus 1.25x. All right, what do? We add that to both sides. We subtract 18 from both sides. So over here, that cancels and that cancels, and we get 2.5x equals 50.5 minus 18, that's 32.5. And so what does x equal? 13. Everybody okay with that? What do you think? Sound good? Okay, so that tells us where the location of the plastic neutral axis is. So let me sort of redraw that down here because I kind of want to make a point about that. All right. You all don't necessarily have to do this. So what did we get? Let's see if I can draw that out. So really it sort of looks like this. And this dimension here is 13 inches, and this dimension is 5, right? So how far is it from the bottom to the P&A? What is that, 6.75 inches? Would that be a fair statement? Okay, just keep that in mind. Just keep that in mind. Now, in order to compute ZX, it's pretty straightforward. We're talking about moments, right? So we need areas times moment arms, okay? So what I'm going to do is this. I'm going to split this essentially into 4 shapes, okay? And for each of those shapes, I'm going to compute the area, and I'm going to compute the moment arm, okay? So let's sort of chug that out. Let's start off with this shape here, this flange. What is the area of that shape? Okay. So, well, I'm going to write it like this. 12 times 1.5. But you're right, it is 18. Now, how far is the centroid of that shape from the plastic neutral axis? How far is that? And a way that you could state that just, I guess, a little more symbolically is to say 13 plus 1.5 over 2. Would that be a fair statement? Okay, plus. All right, now let's do this shape. All right, so what is the area of that shape? It's 13 times 1.25. Is that a fair statement? How far is that from the centroid? Or how far is that from the plastic neutral axis? The centroid of this shape to the PNA. How far is that? 13/2, right? Plus, and now let's do this shape. So what's going on here? So this is 5 times 1.2, whoop, pen got away from me there. 0.25 times what? Say it again. 5/2. And then finally, we have this shape down here. And so that is 16 times 1.75 times what? Is that a fair statement? So you can do this however you want. You can do each of those products separately and then sum it up, or you can do it all together. Like, it doesn't really matter. You can do what you want. But somebody chug this out and tell me what they're getting for ZX. While you're doing that, I want to draw something out on the board just so we have it. No, because you're taking absolute values. If you want sort of a physics, relation to that, let's say you're looking at a beam on the side and you cut a section, you're going to have forces in compression and forces in tension in opposite directions, but the moments are all going to be the same. Does that make sense? That's a good question. And so 533.25. Do I have a second on that? Anybody? Okay, all right. What are the units? This is a section property, and it's specifically like a plastic section modulus. And anytime you have a modulus, it's going to be in something like a length cubed. But I know I left the units off, but it's basically inches times inches times inches. Okay? So that's going to be ZX. And then in order to compute the plastic moment, all you're going to do is just take Fy times ZX. And so Fy times ZX is going to be, let's say it's 50 KSI. And ZX is 533.25 inches to the third. What does that come out to be? 26,662.5. Okay, now what are the units? Inch kips. So if I wanted to convert that to foot kips, I would take this and divide it by what? 12. And so what is that divided by 12? We'll say 0.9 foot kips. All right, so we went up here. We said 6.75 inches. That was the PNA. And then we got that ZX was 5, what? 533.25. Okay. Is everybody okay with that? Now, I want to show you something real quick. First off, does anybody have any questions? Okay. I want to show you something real quick. I'm not going to make you all do this, but this is sort of a review just to make sure that everybody's with me on this. So here's the cross section, right? And you all should remember how to do something kind of like this. So what do we have? We have a shape, A, Y, A, Y, I naught, D, I, right? Remember this? So what do we have? The area of that top flange is 12 times 1.5. The area of the web is 18 times 1.25. The area of the bottom flange is 16 times 1.75. Sum that up, right? Y'all with me on this? Am I going too fast? Or okay. So the bottom flange, the moment arm is 1.75 divided by 2. The web is, 1.75 plus 18 divided by 2. That is 1.75 plus 18 plus that. Then right? So if I computed the centroid right here, how would I do that? I'd take the sum of AY divided by the sum of A, right? And that tells me where the centroid is. Well, I get an answer of 9.275 inches. So the plastic neutral axis was only 6.75 from the bottom, but the elastic neutral axis, that's Y bar, and that's 9.28 inches from the bottom, right? So the plastic neutral axis and the elastic neutral axis are not in the same spot. They moved, okay? And they have to move because as you apply that moment, what we're after is equilibrium. We're after that location such that C equals T. So elastically, that place, it's in a different spot than when you're looking at plastic forces. Now, if you're trying to calculate a section modulus, you got to take it a step further. You got to compute your moment of inertia. So we say, okay, this is 12 times 1.5 cubed over 12. This is 1.25 times 18 cubed over 12. This is 16 times 1.75 cubed over 12. This is that minus that. Remember, it doesn't matter what direction we do that subtraction because we're going to square it anyways, right? And so that plus A times D squared. Sum that up. And so our moment of inertia is something like 4910 inches to the fourth. And so do you all remember how we compute a section modulus? We take the moment of inertia and divide it by that extreme fiber distance. Well, in this case, we're going to have two extreme fiber distances. We're going to have the one on the bottom, and then we're going to have the one on the top. That dimension right there is going to be CT. So how are we going to compute CT? We take the entire height minus that. Does that make sense? Is everybody with me on this? So what do we have? We have, here, I'll move it over here. So we have CT. We have CB. So CB is just that. And CT is the whole height minus that. So 1.75 plus 18 plus 1.5 minus that. And then we can compute our section moduli. So the moment of inertia divided by that. Moment of inertia divided by that. So we end up having a section modulus for the top of 410.1 and a section modulus for the bottom of 529.5. 1.4. We always take the smaller one. That's the one that governs because that's going to indicate the weaker section. And that smaller one is always going to be less than ZX, always, okay? Because remember, this is the point at which just the extreme fiber hits FY. This is when every fiber hits FY. So it's always going to have a plastic moment larger than that. Does that make sense? Is everybody okay with, I mean, am I going a little faster or is everybody okay with this? Just a FYI, if you divide these two, you get what's called a shape factor. And so a shape factor will tell you how much moment you can go over MY. So we don't have to do that, but if you divide those two, it'll be like, what, 1.3 something? I don't know. That's your shape factor. Okay. Any questions about that? One of the things you'll find is actually, it's kind of weird. It's actually easier to compute a ZX than it is an SX. Like the elastic section property is actually harder to compute than the plastic ones. I always just found that a little strange, but that's sort of the nature of steel design. Okay. Everybody good? All right. So I want to talk a little bit about beam capacity. And so in order to do that, like let's just sort of map out where we're going. Ultimately, I want you all to be able to design a beam. You have a beam that's 20 foot long, whatever loads on it. You need to be able to select the most economical section. Okay? And so the first thing that we have to talk about is how beams fail. Okay? And so beams fail one of two ways. Okay? They either fail as a function of what we're talking about here. In other words, they reach the plastic moment, or they buckle, okay? And so I want to show you something, and let's see, I don't know if everybody can see this, but I have some steel manuals set up, and I have this rubber I-beam here, and I'm going to set this between these two beams to sort of indicate that we have a simply supported beam. Now, I want you to watch this, okay? If you notice, okay, I'm going to put my hand right in the middle, okay? Everybody's like, oh, let's check this out. Show and tell time. Okay, I'm going to put my hand in the middle, and I'm going to start to press down. And I don't know if you can kind of see it, but if you notice, there's a point when it kind of just wants to turn over. Does everybody see that? Stand up if you need. You all can stand up. Don't be shy. All right, so if you notice, I press down. There's a point when the beam kind of gives up, it kind of gets soft, and it kind of kicks over and twists. Okay, does everybody kind of see that? This is for the people that are here. All right. Now, watch this. This is going to sound kind of weird. Now I'm going to take my hand, and I'm going to put it over here. Okay? All right. Now watch this. Oh, it failed a lot easier. Does everybody see that? In other words, when I was in the middle, I could go all the way down there before it started to fail. But if I put my hand closer to the support, it fails a lot sooner. Does everybody see that? Everybody see how it fails quicker? Okay, the reason why is this, okay? Let's look at the two cases. Okay, so both of these beams have a span length of L, okay? Okay. I didn't change that at all. It's the same beam. I mean, it is what it is. It's also the same size beam. I didn't change material properties. I didn't change the geometry of the beam. The beam is what the beam is. Okay? Instead, what happened was this. I put a load right here on this beam, and I was holding it sort of in the middle. Whereas the other one, I was putting a load maybe like right here. And that's where I was loading it. Okay? What my hand was essentially doing was it was kind of serving as a brace point. Okay? In other words, let's take the case up top. When I was loading the beam right in the middle, okay, I was loading it such that this distance right here, which is what? L over 2, right? We have a name for that. We call it the unbraced length, or LB. Okay? And so this case up top had an LB of L over 2. So we'll put that right here. LB is L over 2 or 0.5 L. Whereas down here, we had something a little different. You know, we had two different unbraced segments, okay? We had this segment right here, and then we had this segment. So I'm going to like just eyeball it, and we'll say that this one was like 0.2 L, and this one was 0.8 L. Does that seem like a fair assessment? So I'd argue that in terms of bracing, the one that we really needed to worry about was this one right here, that this is 0.8 L. And the short sort of real explanation I want to get across is that the longer that that unbraced length gets, the bigger this value gets, the weaker the beam, okay? Just period, okay? If you were to measure the amount of force I put on this beam, if I hold it with both hands, I can go way far down, way down, because I'm preventing it from moving left to right. Like if I do that, I can see that the beam kind of wants to go, like it's a little wobbly, but if I hold it there, if I hold it and prevent it from moving, I can put a lot of moment on this beam, okay? And the reason why is because a beam's capacity or its potential to buckle is a function of the unbraced length. The longer that unbraced length is, the more it's going to want to buckle, okay? So what we're going to do is we're going to look at two different cases for beams to try and not only understand beam behavior, but to navigate the spec. First off, whose are these? Which one's? This one's yours? Okay. Thank you for the props. I appreciate that. Okay. So the first thing that we're going to do is we're going to investigate cases where LB is 0. Okay. And that's primarily to understand the spec and some of the guides. Then what we'll do is we'll investigate cases where LB is not 0. So you'll see how to handle both cases. Now, first off, let's go to fundamentals. So let's talk about LB and make sure that we're all clear on that. So just like columns, beams present a stability issue. They want to buckle. If you take this beam and you start bending it, you will see how it just kind of gives. Like it just stops resisting that load and it just sort of gives. Okay? It's just like a column. If I take a column and I present a compressive load, it just sort of gives. Okay? That just sort of giving is called buckling. We'll pass that around in case y'all want to mess with it. Just please don't hit your neighbor with it. Okay. Yes, please no violence. I want tenure. Now, oh God. Just remember, we got a final in here. All right. The two different types of buckling are different, but there are some behavioral similarities. The longer the unbraced length, the weaker the element. In this case, the weaker the beam. Now, in this example, I was just holding it with my hand and preventing it from moving left to right. But what actually provides bracing? Well, first off, if I have a beam that's part of a floor slab or a deck slab in a bridge, how do we cast that? Y'all in bridge engineering or in senior design know exactly. All right, y'all in senior design, aka bridge engineering light, y'all know exactly what I'm talking about. One of the tasks given to the senior design teams, depending upon timing, is to try and lay out shear studs. When you cast a deck on a highway bridge, and this is true in buildings as well, there are these shear studs that look like really, really big nails that are welded to the top of the I-beams that once you cast the concrete, they lock together. Another thing that does is it provides continuous lateral support. So if we were looking at this example, it would almost be as if there was a hand everywhere along that beam. So for cases like this, we say that LB equals 0. And in cases like this, buckling isn't really an issue. We don't really care about buckling. All we're caring about is the beam being able to reach MP. So this is a very real instance of a possibility for LB equals 0. Another possibility is maybe you're not looking at the studs. Yes? That's a good question. I mean, so the question was, how far apart do you space them? I'll say two things. So spacing shear studs is a discussion in and of itself. It's a function of one of two things, either strength or fatigue. Whether or not the studs have adequate strength to transmit that shear, or whether or not they're going to behave well during fatigue. I'd say in bridges, you got more than enough strength. Strength's not an issue. It's always fatigue. And in practical consideration, in practical projects, whether you're looking at a building or a bridge, even if those things are spaced like a couple feet apart, that's still enough to effectively consider LB equals 0. And for now, I'm just going to have to ask you to trust me on that, because when we start looking at beam buckling, it's going to make a lot more sense later. I don't want to start getting into too many details, and I want to ease you into it. Trust me. Okay, so this is one instance of continuous support that you can get in a real-life system. Another is something like this. So here's what a floor framing system looks like. And so if you're looking, for instance, at this girder, let's say you're not considering, let's say you don't have studs welded to the girder, you only have studs welded to the beams. Well, this beam, is experiencing all that load, or this girder is experiencing all this load, but the beams framing into it, they're serving as brace points to prevent that beam from going left to right. So that is a potential bracing element. Also, here's another thing. Even if these beams and girders do have studs on them, well, they still have to be able to hold up the weight of the wet concrete by themselves. So they're still going to experience some point in their design life where they're discretely braced, not continuously braced. We're going to do continuous first and then discrete later. A third option, and this is definitely something you'll see in a bridge system, is if you have cross frames framing into the girder. So for instance, if you have, give me one second, if you have a system like this, this girder is discretely braced at each one of those points where a cross frame is framing into it. So more cross frames equals stronger girder, but it also equals more cross frames and more stuff to fabricate, and more stuff to put together, and more welding and all that. So it's an economical trade-off. Yes? That's true, but it's an interesting question. It's actually it was a topic of research a number of years ago to ask how much lateral support do the SIP forms actually provide. Some, but really not enough to be considered practical in most instances. There are some cases where SIP forms would generate lateral support, but it's a loaded topic, and the short answer is no, I wouldn't consider it in most practical instances. It's not 0, though. I will say that. All right. Does this sound good? All right, anybody got any questions about this concept of LB? It's kind of important, and I want to make sure everybody understands it. Okay, now, if you're designing a beam, if you're designing a beam in a building, let's go back to the spec, and let's make sure everybody remembers some of the anatomy of the spec. Remember when we were looking at tension members, remember how we were in Chapter D of the spec? And when we were looking at compression members, we were in Chapter E. Remember with connections, everything was in Chapter J. So with beams, there's actually quite a few chapters that we have to look at, but a lot of the provisions are pretty straightforward. We have Chapter F, which is design of members for flexure, so this is all the moment stuff. We have Chapter G, which is design of members for shear. Right now, we're just going to use a design aid to just look up the shear capacity, and then later on we'll ask how do you compute it. And spoiler alert, shear tends to not matter a lot in building design. And that's just because the way that we manufacture rolled beams, you're going to see when we start doing problems how shear really never is an issue. It can be in some instances, and it definitely is an issue in bridges, but in buildings, for the most part, it doesn't matter. For serviceability, i.e. deflections, we look to Chapter L. So there's a few different chapters of the spec that we're going to look at. And I want to sort of boil it down a little bit. Before I get into the spec provisions, though, I want everybody to turn to page 3-208. You're going to look at this page and you're going to go, now I see why Dr. Mike didn't give us this at the beginning of the semester. All right, so if you look at page 3-208, for those of you who remember this from concrete design, you should remember us having something familiar in concrete design. I used the ones from the wood spec in concrete design just because I thought the images and whatnot looked pretty. But this is actually in the manual. This is the shears, moments, and deflections for very basic loading scenarios. There's a lot of really good info here. The big thing I will mention, and I say this to anybody, whether it's concrete design, steel design, what have you, these are very useful aids, but they're just aids. Some of forces and some of moments will tell you all of this stuff. So if you're confused about the formula and you're like, I can't get the formula to work, then don't use the formula. Break out, calculate reactions, draw a shear diagram, draw a moment diagram to get your moments. These are just tools to help you, so it's just something to keep in mind. All right, now, I'm going to call it after this, and then we'll get into spec. Do you remember in columns how we talked about local buckling, the idea that the flange could buckle or the web could buckle before the whole thing does? Well, the same thing is possible with beams because you have something in compression, things in compression like to buckle. Now, that check theoretically seems a little more complicated with beams, but in action and during actually doing a design problem, it ends up really not being that complicated, and it usually ends up not being that big of an issue if you're using a rolled shape. The long and short of the way that we handle local buckling for beams is that when we looked at columns, we had really just sort of a binary decision. Do we have to consider local buckling or not? And that was it. Well, for beams, we have 3 different ranges. It's whether or not the flanges are compact, whether or not they're slender, or whether or not they're somewhere in between. And we call that somewhere in between non-compact. So when we look up the appropriate ratios, we have 2 different options. See, with columns, we just had one. We're looking at the flanges, here's our ratio. We're looking at the webs, here's our ratio. For beams, there's 2 ratios. Now, I have a star on this, but you actually don't really need to tab it, because if you turn to 16.1, I think it's 17, there should be a tab already there for the columns. And this is the table literally on the next page. So if you look at the header, this table is B41B. It says members subjected to flexure. And then the table next to it should say B41A, members subjected to axial compression. So it's either on the page on the right or it's on the previous page, the one behind it. But the long and short of it is when we do beam design problems, we're going to just be looking at the lambda p values. In other words, if your web slenderness and your flange slenderness are less than these values, then you're good, which 99 times out of 100 is going to be the case for the beams and columns that we look at. The only reason that I harp on this stuff is because if you're looking at plate girders and you're looking at bridges, this might not be a guaranteed, and you actually have to go through and compute this. Okay. All right. Let me summarize. Let's see what time it is. Oh, I thought I had less time. All right. Let me summarize the capacity for continuously braced beams, then we'll call it. So I'm sorry. We got a few more minutes. So how do you compute the capacity of a continuously braced beam, one where buckling isn't an issue? It's the plastic moment. It's just Fy times the section modulus, just like what we did in the last example. Now, the safety factor or your resistance factor is 0.9 and will pretty much be 0.9 for everything that we do with bending. There are some instances with shear where phi is actually 1. But again, shear's not really a big deal. We're just going to look that up anyways. So continuously braced beams are governed by their plastic moment capacity, the yield stress, and the section modulus. One of the most useful tools and aids that we're going to use in this class is table 3.2. Okay? I want everybody to turn to table 3.2. This is some good stuff. Here's table 3.2. There's a lot more going on this table that meets the eye. I mean, there's a lot of info packed here. Some stuff you probably don't recognize, but that's okay. We'll digest it later. Okay. First off, notice again, like many of the design aids that we use in this class, there's ASD and LRFD. So ignore the green numbers. We're only going to use the blue numbers. Now, for now, there are a few quantities that I'm going to ask you to ignore. You'll understand what all of these quantities mean very soon, but for now I'm going to ask you to ignore them. And which ones am I going to ask you to ignore? I'm going to ask you to ignore phi-MR. I'm going to ask you to ignore the beam factor, phi-BF. I'm going to ask you to ignore these two anchor lengths, LP and LR. You don't know what those are yet? You will. Don't worry. Okay? Now, first off, if you notice here on the right, what is phi VV and X? What do you think that is? It's the shear capacity. So for now, we don't need to look up the shear capacity for any of these sections. We can just look them up. Okay? Phi MP, that's your plastic moment. ZX, that's your plastic section modulus. We have the moment of inertia here as well. Now, upon first glance, it might seem a little weird the way they're organized. Like if you look at the shapes, we have a W27 by 146, then we have an 18 by 192 and a 30 by 132. That doesn't really make a lot of sense. But if you look at the ZX column, it makes a whole lot of sense. Because basically what happened was this. You have a shape in you have an Excel sheet that lists all the shapes in the manual, and you just go to sort by columns. Remember that in Excel? You can sort by columns, and you just sort by ZX. Okay? So if you look, for each of these shapes, the ZX is decreasing. Okay? Now, the other thing I want to note is if you start flipping through this table, do you see how the ZX, or the sections are in chunks? Like you'll see a group of 5, and then a group of 8, and then a group of 6, and a group of 4, and a group of 12. Y'all see that? Okay. What can you tell me about the top row for all those groups? They're bolded. Now, here's the thing. Why? Why is the top row bolded in those groups? It's the lightest. Take a look at this group here on the slide. Of all of these sections, what can you tell me about the W33 by 130? It's the lightest out of this whole group. Okay? So that's how the ZX table is organized. They just sorted by the ZX columns, and they broke them off into chunks where you had these economy sections, the ones that are the lightest. So I think you can probably understand the design process. It's probably already been spoiled for you. If you have a beam and you need to design, you basically just solve for your required ZX, find that group. Let's say the required ZX is 430. Well, I could pick the 233, but instead just go up and pick the next lightest one. Okay? And so what you see here is a table that's organized by the ZX, by the plastic section modulus. This is a very useful guide for continuously braced beam design. It is also a pretty useful guide for discretely braced beam design. The reason why is because this phi-MR and this beam factor and these two anchor lengths and whatnot, they're going to become pretty important when we look at discretely braced beams. For now, we're not there, so you can ignore them. We'll define what those are later. Now, that's all I've got for you. See you on Wednesday.